Here on Chalk Talk, we talk a lot about the unsung heroes of electronic design. The crucial components in your bill of materials that just don't get enough credit. And today's Chalk Talk is about one of those components: spacers. Traditional spacers often come with significant drilling costs, assembly complexity, and take up valuable board space. But SMT spacers can solve those issues and include fully automatic assembly. Want to know more? All right, because that's exactly what we're talking about today. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Ameer Elatrash from Würth Elektronik and I explore the challenges of traditional spacers and how SMT spacers can help solve these issues. We also investigate the reflow profile of SMT spacers and the variety of SMT spacer solutions offered by Würth Electronic. And before we get started, don't forget to click that link. There you can find even more information about this topic from Würth Electronic. Hi, Ameer. Thank you so much for joining me today.
Thank you. Pleasure to be here.
Excellent. Okay, so we're talking all about SMT spacers, but Ameer, before we dig into the details, why are we talking about spacers today?
Spacers are one of those parts I think that a lot of engineers don't really think twice about. I would say mainly because on the surface, they seem kind of boring. It's just a little piece of hardware that holds two boards apart, but they're actually doing a lot more than that. Anytime you have a stacked PCB or a display mounted over a board or a daughter card sitting above a motherboard, you're going to need a spacer. And it's not just filling space, it's actually a load bearing structural element in the design. So I like to think about it like building a house. Your PCB is the floor, the spacer is the pillars, and then your second board or enclosure is basically the second floor. You can have a really beautiful design and great architecture, but if your foundation is weak, eventually the whole thing comes down. And it's the same idea here. If your spacer isn't selected or installed right, vibration can lead to board flex, trace cracking, your connectors might not align, and over thermal cycling, if they're not installed properly, the board stacking tolerances can gradually drift. So your whole stack starts to lose alignment over time. So that's really why we're talking about spacers. They may seem like a small mechanical part, but getting them right at the design stage can prevent a lot of failures in field when it's most important.
Ameer, when it comes to spacers, what are the biggest issues in traditional spacers?
I think when most people think of traditional spacers or standoff, they're usually thinking about the part that gets pressed in or threaded in through the board. And these are still a great approach, but it comes with four real costs that add up quickly. The first cost is drilling. Every hole becomes a design constraint. It adds a fabrication step, and it takes away inner layer routing space that an SMT only board could keep. The second is the assembly complexity. Press fit or threaded standoffs need their own installation step outside of the SMT line. So now you're adding in manual labor and another process step. And third is board space. Through-hole barrels and clearance zones eat at the layout on both sides of the PCB. Lastly, it's really a legacy design approach. Traditional standoffs were built for a manufacturing era before high-density SMTs became the norm.
How do SMT spacers help solve these issues?
This is where SMT spacers start to make a lot of sense. Instead of drilling extra holes and adding manual process assembly steps, you can place and solder the spacers in the same pick and place and refill process as your other SMT components. That's going to give you a few advantages right away. You get a fully automatic assembly with faster and more repeatable placement and better process consistency because the land pattern and stencils are specially designed for reliable solder joints. You get to keep both sides of the PCB more usable because you're not dealing with the traditional through-hole barrel blocking routing space. And one thing that I learned pretty quickly when I was designing in my first SMT spacers is that it's not just about the convenience. The mechanical strength of SMT spacers is real. They're designed to provide strong holding forces with solid pull-out strengths and threaded torque when the joint is designed correctly. And lastly, from a business standpoint, you really have to look beyond just the price. Even if the SMT parts looks more expensive up front, the assembly math changes pretty quickly when you factor in the speed, which is about 0.8 seconds per unit versus 30 seconds for the traditional hex spacer, which is roughly 37 times faster. So from our internal assembly benchmarking data, the economic crossover is around 765 units. So at that amount of units, the price starts to break over and actually starts to become cheaper.
So, Amir, what kind of spacer solutions does Würth Electronic offer?
Yeah, actually, we have quite a lot. We really tried to cover pretty much every mounting scenario. At the core, you've got external thread, internal thread, through hole, and reverse mounting options, and those you can see at the top row of this slide. Beyond that, we have more application specific solutions. The WPSMRA is the right angle version for perpendicular board mounting. The WASM SSR gives you a tool free snap rivet style option. And then we have mountain buttons and accessories like the WASCAP and the WASCRW, depending on what your assembly needs. And there's also an extended option, which is the WASMSA, which is the automotive grade series for more demanding applications. So whether you need threaded, pass-through, reverse mount, right angle, tool-free, or automotive grade fastening, Würth Electronics has spacers built for that use case.
All right, so Amir, talk to me about the different options for fastening.
Sure. So across our portfolio, there's basically three fastening approaches here. The first one is through hole, which is the WASMST on the left. And in this case, there's no threaded engagement in the spacer itself. It's a bolt or pin that passes through the bore, and the spacer is being compressed, not torqued or twisted. So the fastener provides the clamping force, and the spacer's job is to set the distance and carry that compression load. The second option is threaded fastening, which is the options I show in the middle. Here, the screw actually engages the spacer thread, so now the spacer is being torqued. This means that the solder joint underneath has to resist that load, which is why the pad design and solder joints quality matters so much on these parts. And the last option is the screwless tool-free fastening, which is a snap rivet on the right. This one has a screwless snap-in option, so there's no threading or tools required during fastening. The retention comes from the neck geometry itself, and the snap feature creates a mechanical hold and gives you shear resistance, which makes it a really practical choice when you want fast, tool-free board-to-board attachment, or in some cases, if you want disassembly to be easier as well.
What about spacers for automotive applications?
Yeah, definitely. For automotive, we have a dedicated family called the WASMSA. It's the automotive grade member of our SMT spacer portfolio. The reason we gave this product its own family is because automotive is really about qualification and mechanical robustness. These spacers have a greater solder pad surface area with more robust joints. This gives you better resistance to shock and vibration and a higher load capability with improved shear performance. I would say this family is not just for automotive in the narrow sense. It's a really strong choice anytime your design needs a little bit more mechanical margin, especially when shock, vibration, and load are a real concern. I would say if this product's going into a more demanding environment, whether that's automotive or any application with a tougher mechanical conditions, this is a series I'd want engineers to keep in mind.
So, Amir, what kind of accessories do we need for these solutions?
We have a small accessories ecosystem here, and it really addresses two common design needs: isolation and faster assembly. On the left, we have the distance cap and the plastic screw. This combination is the right answer. We need electrical insulation, and in the case of the cap, thermal insulation as well. It also helps you create an intermediate height without changing the metal spacer itself. So it gives you a little bit more flexibility in your mechanical stack up. In the middle, we have the snap rivet combo. This was all about a tool free assembly. It's a completely screwless option and it's fast in mass production. And it's also detachable. Because the body is nylon, it also gives you inherent electrical isolation. And even though it's plastic, it's surprisingly strong in shear. And then on the right, we have our mounting button. This is the one to think about when your priority is quick and easy mounting. It works with all M3 types and it has a high retention force. And if you ever need to remove it for service, it can be unscrewed with a Phillips screwdriver.
So, Amir, how do these fit into the normal SMT line?
From a manufacturing standpoint, these are designed to be true SMT components. Across the SMT spacer portfolio, these parts are supplied in tape and reel so they can go straight into a standard pick and place flow with direct SMT line compatibility. We have three standard packaging variants: R, RR, and RX. The R version uses a polyamide tape to give the vacuum pick nozzle a flat surface to grab onto, and it features a notch for instant removal once that reflow process is done. The RR version is the same, but without that notch. And then the RX version ships without any placement aid for designs where the top geometry is already flat enough for the nozzle to grab onto. We've designed these parts to accommodate different manufacturing lines and different visual sensing conditions. And our FAEs are more than happy to help ensure this if you ever run into any issues with that.
All right, so what about the reflow profile? Can you talk a bit about that as well?
Sure. Usually there is no change needed. These parts are qualified for standard SMT reflow, and they work with a standard lead-free profile and have been validated up to 250 degrees Celsius peak through 5 reflow cycles. They're also RoHS and REACH compliant. So from a manufacturing standpoint, that's the reassuring part. Multiple reflow passes are fine, and the spacer itself is not what forces you into some special one-off process. The one thing I would recommend to pay attention to is thermal mass. The spacer body is steel, so it takes a little bit longer to heat than the tiny passive components. And on a mixed board, those small passives can get to peak first while the spacer joint is still trying to catch up. And that leaves the spacer under soldered, even though everything else looks okay. So if you need to tune your profile, it's usually not a full redesign. It's more about giving the assembly a little bit more time in that soak region, which is around 150 to 180 degrees Celsius, so that the heavier spacer and small SMDs can come up more evenly before the peak. So I would say the takeaway is pretty simple. Start with a standard lead-free SMT profile. Know that the multiple reflow cycles are supported, and keep an eye on that thermal balance when you mix the heavier steel spacer with the smaller parts nearby.
So, Amir, how does a plated through hole compare with a non plated through hole?
I would say this is one of the most important design rules in SMT spacers. For the borehole, you always want it to be non-plated. If you use a plated through hole, solder gets pulled into the hole instead of staying on the pad where the joint is supposed to form. And once that happens, a whole chain of problems starts. First, you starve the joint because you've lost solder paste down the hole. Second, on the threaded versions, tin can wick up into the thread by the capillary effect, which makes the screw engagement harder and reduces the thread usability. I've showed a photo of this in the slide. Third, with less solder on the pad, you lose retention, and that means lower shear and pull-out performance because the joint is no longer forming the way it's designed to. And fourth, you can also lose alignment. With the wrong hole construction, the spacer is more likely to float off the center during reflow instead of staying centered on the pad. So with a non-plated through hole, the solder stays where it belongs, the thread stays clean, and your joint keeps its mechanical performance, and the spacer stays centered. So the rule is simple: non-plated through hole only, always.
Okay, so walk me through the design in process. What steps does it include?
The good news is the design in is actually pretty easy. There's 5 rules to follow, and there are things that most directly affect the wetting quality and the final joint strength. The first is the landing pattern. I would recommend you use the datasheet footprint exactly. Don't scale it, don't try to clean it up. I wouldn't try redrawing it from memory. That ring controls the solder volume and the meniscus around the base of the spacer, and that meniscus is the big part of what gives the joint its mechanical strength. Second, use non-plated through hole only. This is a hard rule we discussed in the previous slide. You really don't want solder to get pulled in where you don't want it to. Third is the stencil aperture. We recommend 150 microns using a segmented or spoke style pattern. For internal and through hole parts, we recommend you use a 4-spoke version. And for external thread parts, it's recommended to use the 2-spoke version. Fourth is your keep out zones. We recommend you keep nearby components and vias away from the solder pad area. You want heat to evenly distribute around the full pad ring so that the joint wets symmetrically. If one side is crowded or thermally disadvantaged, the joint quality won't be as consistent. And fifth, use the recommended footprints from the datasheet or product page. Don't try to redraw these yourself unless you have a very specific reason to. The pad geometry, stencil design, and spacing are meant to work together. So if you start changing one piece, you're also changing how the whole joint forms in reflow. So if I had to leave engineers with one takeaway from this slide, it would be that pad geometry and stencil paste thickness matter the most. Get those to your right, and you're going to be setting up your joint for success.
All right, so Amir, what kind of performance metrics should we consider for these kinds of solutions?
So we look at 3 things: shear, pull-out strength, and braking torque. So basically how hard it is to push the spacer sideways, to pull it off the board, or to twist it until the joint gives. What's nice is on the slide that I'm not just showing you the numbers, but I also show the test jigs for each case. So you can see how the shear, pull, and torque data was generated. You can see the averages for the M3 version showed in the slide, and these are published test results from a 30 sample lead-free solder testing, and they're not just estimates. So you can see that even at M3, these are pretty serious mechanical joints. And just for a little perspective, these are just the M3 numbers. If you go up to M5, the published averages jump up to like 196 newtons in shear. So that would be able to hold a small motorcycle engine before shearing.
What do you think are the biggest benefits that Würth Electronic brings to the table here?
I think the nice thing here is that a lot of the work is already done for the engineer. The performance data is published, the parts are built for standard SMT processing and validated through 5 reflow cycles. And there's also FAE support available if you ever need help getting the design in right. It's also a production-ready solution. The portfolio covers M1.6 through M5. It's available in tape and reel, and there's footprint and profile guidance, so it fits pretty naturally into the SMT line. And if you need an empirical solution, we're more than happy to accommodate that as well. And from a sourcing standpoint, it's pretty straightforward. Through Mouser, you have same-day shipping, an active portfolio with new and extended series, and a full parametric search. So if you're looking at SMT spacers, you've got solid data, parts that are ready for production, and a pretty easy path to getting the right part into your design.
Excellent. Well, Ameer, I think that's all I have time for today. Thank you so much for joining me.
Awesome. Thank you.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Würth Electronic. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.